Welcome back to the next video, everybody. Today, we're going to be covering another key result needed for the proof of Fermat's last theorem, a very deep theorem of elliptic curve theory called Mazur's torsion theorem. So let's get into that. So recall, if we take E over Q a semi-stable elliptic curve, then part of theorem 1 from the previous video was that rho bar EP, the mod P representation attached to E, is absolutely irreducible for all but finitely many P. So the question is, which primes P are we looking at? So the next result is considerably deeper, and that's Mazur's isogeny theorem. And here's what it says. Let E over Q be any elliptic curve. Then three things are true. If P is a prime larger than 163, then rho bar EP is irreducible. Okay. If E is semi-stable and P is a prime that's bigger than 7, then rho bar EP is irreducible. And if E is semi-stable and rho bar E2 is just the trivial representation, then rho bar EP is irreducible for all primes that are bigger than 3. Okay, so for a proof of this, you can see Mazur's rational isogenies paper, which I'll call MRI from here on out, theorems 1 through 4. You can also see Sayre's SPG paper, proposition 21. But then in chapter 17 of my notes, I will be talking about this proof as well. All right, so corollary, let's let E over Q be a semi-stable elliptic curve. And then rho bar EP is surjective for all primes P at least 7. So the proof of this is you use the isogeny theorem to get irreducibility. And then you use a result of Sayre from SPG, which says you're either surjective or irreducible for these primes as long as you're semi-stable and as long as you're looking at the mod P representation. Okay, you can also see MRI theorem 4, and then I will be discussing this result in chapter 7 of my notes, although I've already put the video up that actually discusses this result very recently. All right. So let's keep going. So let's take an elliptic curve E over Q. Mordell's theorem for elliptic curves says that EQ, the group of Q points on E, is a finitely generated abelian group. So you can see Silverman 1 for a proof of this. But the second you have a finitely generated abelian group, you have the structure theorem, which says that it must be the case then that if this group is finitely generated, that it breaks down into its torsion part, so all the elements of finite order, direct sum R copies of Z, where R is an integer that's non-negative, okay? And this R here is called the rank of E. And if you've looked into the Birch-Swinnerton Dyer conjecture, you know that all things considered, we know very little about the rank. But there's kind of two pieces of interest here. There's the torsion subgroup, and then there's the rank. So let's ignore the rank for now, more on that later. And let's ask, what can we say about the torsion subgroup? All right, so that's Mazur's torsion theorem. Here we go. The following result can either be proven directly. Mazur does this in his Eisenstein ideal paper, his famous Eisenstein ideal paper, MMC, or it's actually a relatively easy consequence of the isogeny theorem we just covered. And in MRI, I believe it's Sayre that gives a quick proof that the isogeny theorem quickly implies the torsion theorem. And I will be discussing both proofs in chapter 17 of my notes. So here's the theorem. Let E over Q be an elliptic curve. Then the torsion subgroup of the Q points of E is isomorphic to one of the following 15 groups. Z mod NZ, where N is between 1 and 10 or 12, so you skip right over 11. Or Z mod 2Z cross Z mod NZ, where N is 2, 4, 6, or 8. So this is a very deep result. This is a very hard result. We will need this result coming up pretty quickly in the proof of Fermat's last theorem. Okay, next video, I will begin looking at some of the local properties of the Galois representations attached to elliptic curves that we didn't necessarily specifically point out, but which follow very quickly from, in general, theorem 1 from the previous video. So I'll see you all then, and thanks for watching.